So thank you all for joining our CSM seminar. We are very happy to have Dr. Mumtaz here with us to give us his opinion and vision on 6G, new trends, standardization, and so on. I imagine you all know Dr. Mumtaz. He is an outstanding member in COMSOC. He is actually a distinguished lecturer at COMSOC and at ACM, recipient of many awards, and in charge of many roles as vice chair for standardization and also in the Green Communication and Computing Society, participating in operators and manufacturers. So giving talks in many conferences with more than 300 technical papers in journals and conferences. As I said, he is outstanding member in the community with an H index of 61. So we will enjoy the talk with his vision on how the 6G will move on. Okay, so thank you, Dr. Mumtaz, again for accepting our invitation. It is our pleasure to host your talk. And thank you for agreeing to record the lecture. So we will later post it on our CSM channel on YouTube. So with no more saying, Dr. Mumtaz, the floor is yours.
Thanks, Hazar, and also thanks to the committee CSIMQ for inviting me to present myself today. So I hope you will enjoy the talk. If you have any question, please feel free to ask at the end of the presentation. So let me start now. So today I will talk on the vision, requirement, technical challenges, standardization, and implementation for 2020. Most of the things you already been seen in any other talk, but some are my own idea and my own view that how 6G will look like in next 5 to 10 years. But again, after 2030, when its real implementation can be seen in this world. But now most of the work will be done from the academia, where we have some vision, but still in standardization, still we haven't started yet. It will be starting 2025 afterward in the release 17 or afterward 18 when they are start going to start standardizing now, both in standalone and non-standalone mode. And then I will talk on megatrend toward 6G. Then third part will be 6G service classes and scenarios, and what are the 6G requirements, and what are the 6G candidate technologies. And lastly, I will explain mostly from standardization what are the timelines and what technology will be a part of standard in the future releases, and also a business model for the operator as well to motivate them that if they want to shift from 5G to a 6G, so which kind of business model they need. So at least you understand that. So this is a customer. Then we have a spectrum which can be on millimeter wave below 6 gigahertz, or you can go over 6 gigahertz, and we have certain bandwidth here for the pictoriality. I'll just mention 140, but it depends upon where you are deploying. And then we have the E node B, which is the name coming from the 4G, but in the 5G they call G node B. So just is the name, and our functionalities are a bit different. So the RAN, radio access network, and it can be given by any vendor. In this picture I mentioned Huawei, but it can be in the vendor as well. Then we have a transporter, someone third party who is arranged for the operator. So you can see that is a mixture of different things. For example, core can be from Nokia, base station from the Huawei. So this is you can see that now we are mixture of the vendor and operators are using different infrastructure. So Portugal Telecom, which is now converted to the French one, Altis Lab, and you can see that the signal strength. So most of the region is covered by the Vodafone, which quite good signal strength of 88 dBm. So it is not so big country, but the Vodafone covering most of the country. And then you have Nosh, and then you have other two operator as well. So MEO is now owned by Dutch Altis Group with around 40% of share in the Portugal market. Altis began to working with Ericsson, so I think above around to 5.6, they will deploy there as well. But again, this is the political issues going on here in Portugal. Okay, so to recap about 5G, what we have been done from last 10 years when we started 5G in 2012, when we start from the academia, as we started 6G as well. So in the academia, there's a lot of work can be done, and then we start standardization in 2017 with 3GPP, and it's fully standardized in 2020, and now till today we are deploying it in a various shape, either standalone or non-standalone. So as you can see that from on that time and enhanced capacity, these are the three use cases which are predicted by ITU on that time, and there are some certain KPIs associated with them, and then 3GPP is working on these three use cases and propose different technologies to make them a reality for the future which we are now. So some of the technologies you can see that work a lot on massive MIMO, multi-connectivity, and they have reliability, device to vehicle or device to device communication, and other technologies as well. So if you see that one of the technologies, some of the technology which is really groundbreaking, everything best you can achieve in terms of latency, throughput, separate efficiency, energy efficiency, everything. Even you combine all of the gain of all the technologies, you cannot reach the gain of small cells when you decrease the transmitter and receiver. This is the one of the highest you can achieve. So that's why we are going toward very, very high frequencies now, millimeter, terahertz in 6G. When you go for the high frequencies, your wavelength become shorter, so you cannot transmit for the long range. So your cell size automatically shrinks, so your capacity will go to increase. But again, the coverage will be issue. So for the coverage, we have to come up with the lower bands, and for the data communication, we can transmit with the higher frequency. So this is small recap about 5G. So let's go with the mega trend. Depending on, as I explained you, the first it will be coming from the academia, and also some of the white papers coming from different our manufacturer, vendor, and different ecosystem for the mobile manufacturer. So if we summarize them, so they are connected machines, where machines as the main user. Work have been started in 5G, but this you can really see the real power in 6G, and then the AI for the voice communication. AI already started in 5G, but now the main idea is how to standardize AI. What are the interfaces we need to standardize, and the AI work well very at transport layer core part, but we want to come AI at the bit at symbol level, how we use AI at the MAC, the physical layer. What are the main enhancement we need? Because at the physical layer, mostly we have very nice mathematical equation. We have a lot of closed form expression, so we don't want to play with them, because we already optimize our network at physical layer. So we want to see that what will AI bring more to the physical layer, because once you have a closed form expression, so we already optimized one. So we need to see what are other sectors where AI can be benefit. And then we talk with the openness. So at the core part, we already have the open our source, open cloud, open core part, but now we are moving toward RAN part. So the concept of open RAN, virtual RAN is coming now. So that is also quite new, at least when you want to standardize these interfaces as well. And then we have social goals and mobile communication. So like ethics, where you use a lot of AI, so ethics are very important. They need to be standardized, and plus every day we are producing a lot of apps are coming, a lot of communication technologies are coming. So it's important to propose some of the social goals, and what are the legals, and what are the valid data between the mobile communication. So it's important to make our society secure also. That is the, I don't have a time for this presentation today, but this is the where we have the Society 1, Society 2, Society 4 concept. So we are in the Society 4 now, but we are moving towards Society 5, where we define our society goal, which directly map with our mobile communication. So I will not talk this in this presentation, but I will talk first 3 bullet points. So before going to 6G, it's important to see what will happening very quickly, that happening our generations of telecommunication. So you can see that after every 10 years, we are changing our telecommunication generation. That is how our telecommunication work. So for 4G, we spend 10 years, 5G, we spend 10 years, 6G, also spend 10 years as well. So in 1980s, you can see that when we start our telecommunication, so more or less not telecommunication, but our networking, where you have the important is a network. We have APRANET, we have network, and you can see that the operating system, hardware, and human machine interface. And you can see that some are valued and some are devalued on that time. Then after 10-year time, then you can see that our APRANET will be converted to WWN, getting some valued and devalued, and also our network start getting valued and devalued as well. And then we can see that we have CPUs are coming, we have input devices are coming, output devices. We can see much better what we are seeing 10 years back on that time. And then our telco, our mobile operators started realizing the importance of the network. So they are transferring our WW to the telco system. So this means they are putting some of the capabilities of internet inside their network also on that time. And you can see Nokia 3360, very famous phone, was built by Nokia. And then around this is the time where we are on the bed of the 3G, and you can see that everything is getting quite important or devalued as well. And then after 20 years, now you can see very important to see the upper blocks. So you can see that the telco now convert into cloud. So now we are shifting toward the cloud, and the network getting valued and devalued also. And now 30 years, this is the prediction by 2030, that when we are the first release coming in 3G and 6G, you can see that now we are moving into pure data center application, DSPs, which are all running inside cloud. So a network is more like a passive pipe rather than active pipe in network, where you have ATM on that time, you remember, asynchronous network. So now everything is in cloud. And then most of the operating system will be virtualized, and hardware is only via RF part. Most of the base processing will be done in cloud, and our interface will be done into holographic. So you can see that there's a huge journey which we are taking almost 20, 40, 50 years, that we are coming to the cloud part. It take a long time. So that is a vision. You can see that from 1G to 6G we are moving. So in terms of device sizes, it's very also nice picture, which you can see that from the beginning we have very huge bulky website with the transistors almost around 50 nanometer, very big size of transistor. If you can see from left to right, you can see the size of transistor getting small, and your devices are getting more complex and more power hungry. But of course, you get a lot of functionalities from one device. You can talk, you can release some video, you can make video, cameras, everything. But if you go from right side to the left, your transistor side are getting bigger, but again, the capabilities are getting less and less. So that's why people talk, when you talk about Moore's law, that we are reaching the limit. That is the way, because we cannot have decrease more than like 5 nanometer for. Now Samsung is making around 5 nanometer transistor, but we cannot go beyond that part. So this is one of the reasons that we are reaching to Moore's law transistor size. So we are not making so much smaller because of the heat conversion between the circuit and other factor as well. So this is also, you can, the journey we are taking. So you can see that we are here somewhere, but in 6G there is, I don't know what will happening, which kind of set will be available, but it's like a more like a gesture kind of tactile, which is shown by this figure. So we did some more technical part, bit deep on that. So when you have 5G, mostly the stuff which we are doing in our research, mostly we look at network from the two sides, either uplink or downlink, and we are always considering two node. Either we make a solution for the base station, or we are make the solution for our end user. And most of the time you can see that our approach will be very close-minded, because we have expression, we are 6, and partially we are making dynamic as well. But when you can see to the 6G era, 6G only the speed of the light will fix, because that is coming from the physics. When you transmit your electromagnetic wave, this is a fixed speed you need to transmit. But here you have two worlds. One is your real world, one is your virtual world. In the real world, you have different nodes. It's not only the user, you have your verticals where you have different kind of industries. You have big cars, normal human, IoT, name a lot. And then you have the virtual world. This means you need to optimize your both world. What is happening in the real world, you have to make in the virtual world also. So these things will be more complicated and demand more innovative technology. And this virtual world technologies like VR, AR, metaverse, digital twin kind of thing. So we need to optimize both world, and there should be some kind of connection, so which connect these two world as well. So I will show that in my next coming slide. So this is where we say that machine is quite important, because we have to create the machines which can able to process this amount of data when you're connecting this world. So why machines are important? Because machines can do everything which human can do. We have some of our physical limitation the way we born. So, for example, you can make a telescope, microscope, which can see a very tiny object which cannot see by a single eye, or you can go to the James Webb telescope, which is now seeing world which we cannot be able to see now, and they are sending a kind of images from the space to the Earth. Then, for example, human eye can see around 500 megapixel, but after that we cannot see. So we can make our cameras or telescopes which can go more than 100 megapixel also. And there is also some of the differences which can human capability, and you can do machine which is more efficient in that. So along with these lines, machines, so let's talk something on the AIs. I specifically write physical MATLAB because that is the challenge. So if you see that our inference communication, which is coming from time from Shannon 1948 till now, mostly what we doing, we do a lot of source, transmitter, very sequential kind of things, because we know that we have very close form expressions for everything, so we don't need to worry about that. So our system of physical is already quite good optimized things. And a lot of work has been done on transmitting side, MIMO, CISO, and then you can have coding, modulation, on the noise, a lot of work on channel modeling. We do a lot of, and then on the receiver we have decoding, demodulation, zero forcing, MME. So I mean, there's a lot of work done, and we are very well understand that how this system is work. But now the challenge is that now we are moving toward machine learning era, AI, artificial intelligence. So we want to bring AI very close to the bits and symbol level. So we need a transmitter and receiver, but in this way we need to read you that he will learn from the transmitting data, and which part of the learning, how they learn, that is you already know. I'm not going to detail of that. Algorithm supervised, unsupervised, reinforcement learning, predicted learning, these are different methods, but at which level and which data we need to transmit and what are the signaling, that is the challenge. So far, one of the things which you can do is standard estimation, which is a bit faster, but we cannot have a coding modulation, because for modulation already very close form expressions. We don't need to do that part. We have to do where we have a more iteration and where we have consuming more optimization. That part we have to do it. So that is the thing which we need to figure out in coming years. So as I explained in the previous slide, this is also some of the differences between deep learning or AI artificial with the conventional and the 6G, what will happen. For example, in the mathematical model, we need accurate mathematical modeling in conventional system, which we tell using 4G till 5G, but it does not rely on accurate mathematical modeling, because when you don't have mathematical modeling, then you use deep learning to do some optimization. And then in 6G, it's one of the area which we can do. We can have both. We can take help from closed form expression and also the optimization as well. From the design approach is optimizing each module separately, and here they also do each module separately, but in 6G my area is that each module optimized but compute dynamically and easily. So this means that you optimize each or every complete system, or you do dynamically each. But you so similarly, we have other parameters. So due to time constraint, I will not go through all of them. So for example, complexity, we can see that in a conventional system, we have quite less complex here, medium. And of course, when you in 6G, as I explained you that we are going a hybrid kind of approaches where sometimes you're going to combine one or combine two, depend upon your scenario or the use case, the problem you need to solve, so it will be more complex. So another challenge is the lack of interoperability, because when you're going to implement your machine learning, so this means you need to have some data set only for this one. But if you want to train this model for different size, you need to redo again a new data set. So this is a big issue. So this means that we cannot use one model to the another model. So this is also a lack of interoperability. So what if we want in future that we thousand of the system can be learned from one data set. So it's not only just dependence on the scenario, but also it will be generalized machine learning which can be used on every device. There should be a lack of interoperability. So we need to create a kind of open neural exchange so they can use on everywhere. Rather, we teach all the devices one by one. So you can see that it can be at the device level, can be at your eNode level, or can be your transport level, or at your cloud level also. So this means that you have your machine learning on all domain of your network, device level, localized level, or is end to end. So that's what I explained. You have your device, AI, and the end-to-end level. But again, this is the thing which need to be standardized. Of course, in the theory wise, in the academia, it is possible, but we want to see that what are the signaling which we need to be standardized to make that to be a reality for a different player which they want their AI algorithm to be part of the system. So about AI, the AI is now everyone use the AI, but still there is a lot of things which we cannot do with the AI. AI is still lacking there. So if you give them the images, AI will tell you either it's cat or dog or animal, but it will not tell you why it's cat, why it's that. Like a human brain can give you the explanation of that, and with this explanation, he can find new things also. This is one of the biggest problem with AI now, which we need to solve in the 6G. For example, when you do the channel estimation, they will tell you which data you need to send for the data signaling, your pilot or data, but it will not explain you why this will be done, and also it will not give you a suggestion that okay, if you do this, it will get better channel estimation on that time. That is whatever we teach them, they will give you the answer there. So that thing we need to see that how we need to understand the answer of why in the future. So to make our like, for example, if we take the example of the base station that we want to make him very efficient like a human brain. So you can see that our base station, like processing power, can be our like intelligent radio, where he can do the processing. And then if you want to give the eyes, like a human have an eye, he can see the camera. So base station can see with the computer vision, we see the object with the eyes, and then he make the decision here. And of course, if he can send the signals with using the concept of natural language processing, but nowadays we just send 0 and 1 without any meanings, but it's important to give the meanings to that signal. The concept which you're doing now a lot in nowadays is semantic communication, which is giving the meanings, rather we send the bulk of data. So we can make our base station smarter like a human being, human brain. We give a brain, we give the eye, central processing, and with the eye he can see the object, he make decision, processing will be done, then he hand over to another one. So he know that this user is block user, so he hand over another base station can give him the signal as well. So these things we can see that now you can see that we are taking this concept of computational and communication together to make our system more smarter. So semantic communication just getting a lot of attention from last couple of years. So is the main idea is that how we transmit, we need to focus what we transmit. So that was the main idea. Shannon tell us that we can transmit as much as possible according to the channel bandwidth available. So if we go beyond that, we can transmit. But semantic is the meaning that what we transmit, that is the important now, how we transmit. So that will save our lot of energy in the system and also the bit which we're going to transmit. So if you can see that Tesla, who started in 1926, he said that when wireless is perfectly applied, the whole world will be converted into a huge brain. So that is happening now. So we know that with the help of the semantic communication, you can see that this vision will be more easily applied. So we are taking care of both synthetic part of the Shannon and also the semantic. So we are taking care of both of these world from Shannon and Weber. So semantic communication can be in different form. It can be you can transmit with the bit, with the meanings to that bit, that what this bit is going for, or you can also call is a goal-oriented communication with a certain goal. So fundamental system specification is then associated with its a goal within that given time constraint. Either you want to decrease the energy or computational efficiency or increase the efficiency of the system. So you need to transmit that information inside your bit. Rather, you just transmit bulk of data. Some bits are useful, some are not useful. And you can do the own learning based communication as well, which is also a part of semantic communication, and where you have online, where you use a lot of machine learning techniques to reshape your traffic, change coding, decoding, scheduling, etc. And the last part is the wireless channel, which we also control by the intelligent reflected services, which we use that to make our wireless channel more smarter and to give the meaningful information to the channel to transmit from the receiver to the transmitter or transmitter to the receiver. So these are some of the layers which is going to be happen in semantic communication. We have level 1, level 2, and level 3. In the first level, which we have normal Shannon communication, where main idea is to how accurately can be a symbol be transmitted to a communication network. That is what we are using from 1G to 5G. That is our main goal. But now we have second level, where how precisely do the transmitted symbol convey to the desired meaning. So we want to get the meanings. So we create a knowledge base on the transmitter side, we get the knowledge base on the receiver side, and we transmit our data. And if we get some error, we don't need to ask from the source coder like we are doing nowadays. We just check from the knowledge base as well and try to recover that data from here. So it will save after a lot of retransmission and the power and feedback channel also. But of course, there's a lot of other challenges which I'm not going to discuss. This is very high level picture where you can see. So this means we need to design a new semantic decoder, semantic encoder, interpreter, and knowledge base. And in the knowledge base, you need to update your knowledge base, to keep updating by using different learning techniques and also natural language processing. Again, depend upon whether you want to transmit video data, audio data, or simple text. This is all depend upon the scenario, and according to that, you need to update your knowledge base as well. So now let's talk something on the openness. As I explained you that we are now going toward RAN openness. So this is, if you know that we started from 4G where you have DRAN, and then we have Cloud RAN or CRAN, then we have NFC, SDN, and now the concept network slicing ends in the 5G era. So let's go briefly and very fast. So we have the core part where you have application, and core will reside inside one core, and then you have a backhaul, and then you have your digital unit and your remote radio head, and on the maximum capacity of that phone around 75 megahertz is category 3 phones they are using by 2x2 MIMO in 4G. And then China Mobile proposed the idea of Cloud RAN or C-RAN in 2012. And the main idea, they just separate RU with the DU. They put more close to the radio head, and DU will centralize BBU. All the baseband processing will be done here, and then on that time the capacity of our phone will be much better. And then we go to the another level to virtualization SDN, and you can see that now our core will split into control plane, user plane for the core, and your then we have the edges coming, core part and the CU, and you can see that now we change name to RU to the access unit, and you again here you have different devices along with phone. You have IoT, vehicular also. So you can see that we start with the distributed RAN, cloud RAN, now virtualization, and then the next step was the network slicing, which is very much hot topic, was and still hot topic, and a lot of work has been done already in standard as well, where you do the slice the network. So you can see that you have different slices according to your scenario. For example, for voice, you have your control unit should be very close to your access unit. Other will be reside inside cloud, other main cloud. But depending upon scenario, you can shape your protocol stack depending upon the critical, low latency or high throughput as well. So you can see that starting from DRAN, Cloud RAN, now we end up with the network slicing. So this picture, you can see that you have air interface, you have access part, and then you have a core part. So mostly they are emphasized with the hardware and the software. And this is also a part of hardware software. Why I'm showing this? Because if you see on the green part only the 4G, mostly all of work on the same principle. Here the idea is to that if you want to buy hardware from Nokia, you need to buy hard software from Nokia as well. And same for the core part. Is proprietary software and hardware which belong to a one vendor. This is the main idea of showing this picture. So what happened in the mobile tower real life, you can see that we have the antenna upstairs, we have the cables which is coming your BBU and the RU part, where all your signal processing will be done here, and your RF will be done on the antenna part, and then your fiber cable which is connected to antenna to the BBU. And then if you can see more into deep, that if you open that part, you can this is a remote radio head, this is your RF, and this is your common public radio interface which connect, this is mostly common for all the vendors, so they are connecting with your RF to the PBU. But in this case, it's very important to know that this is the hardware which is belong to a specific vendor. This is also belong to a specific vendor, and software, I mean from one of the guys. You have to be buy from same vendor. Okay, so this is my contemporary RAN, which is a proprietary hardware from one vendor, and this is also from one vendor and one vendor software as well. So we cannot do anything; we have to buy from them. And this is the proprietary interface as well. And then what happened in the concept of virtual RAN? The virtual RAN, that this is still belong to the proprietary hardware. And this is proprietary interface. And then now what we are doing here, that now we're going to virtualize it. So we don't need to buy from the specific vendor. We just off the shelf, we like a virtualize. We just have a software and we can use at the off the shelf server. So this is start reducing the cost from different operator. So after virtualize, so we need to do the Open RAN as well. So what happened in the Open RAN, that this part now we are putting to the GPP general processors from the Intels, the cost of the hardware SDRs, and this is from the server from the proprietary. I'll explain the same like in virtual RAN, and this is now also open. So this means what happened now, any software can work on any hardware and any hardware work on any software. So this is more, all the operators are all the vendors are agree on this. So there's already a lot of work can be done on this Open RAN part in getting a lot of attention. And the future will be that you can use a lot of operator will be used that part. So this is just a difference why we use GPP and SAV servers. So general purpose processor is generally called central processing. It performs all computing tasks. Is from the Intel mostly they use, and they are true hardware and software degradation possible in this one also. And similarly, they have their SSP single processor. We cannot do most there. So mostly the work we are using for this virtualization, we use mostly general GPP. And then there is already stuff which is coming in, like modules are available now. Open RAN enabling white box. You can see by the way you are all one in GPP base station. Just explain you, and then but you have a white box RU as well. So this is some of the advantages of the Open RAN and the traditional RAN. So you can see that with the Open RAN you have more software defined, unbundled. You can programmable interfaces and is morely deployment and flexible and is front-all agnostic as well. So you don't need to depend upon the technology like in the traditional RAN. So you see that in the next generation we are going more toward the openness along with the core part as well. So this is one of the interesting example I think is important to give. So just imagine we have a lot of services are running on top of us, like video, audio calling, then we have a core part, then we have transport, and then we have proprietary RAN software and platform. This means this is belonging to a specific vendor and specific software and hardware is the same. And then we have a different hardware as well. Just imagine this is the base station is running. So just imagine if I have a base station running from different vendor, like for example, all running from the Nokia one, and these of the cost servers. As I explained you in the virtual, we don't need to buy, and this is the Open RAN running with version 1. And just imagine if I want to change that, okay, I want to change from Nokia to the Huawei base station, so I don't need to update my software because of thanks to Open RAN, this work will on hardware as well. And similarly, I can change any vendor hardware base station with the same software configuration. So we don't need to worry about that anymore if Open RAN is going to be implemented. And then if I want to update my software, like baseband, I want to update my baseband, some Mac or something, I don't need to change the hardware as it will work perfectly. So similarly, the same concept you can replicate in the cloud domain where you have BBU and RU, because BBU is now dividing into two parts, into say, control and distributive unit and your remote radio head as well. And same thing happened that if you want to change your RU, BBU just need to update the software, it will work perfectly as well. So this Open RAN concept will work perfectly, but again, there are a lot of interfaces which is already centralized by the Open RAN alliances. For example, in this picture, so if you need more, please study that. The main heart of this Open RAN is the rig controller, where they are doing a lot of enhancement with machine learning techniques and other, because a lot of innovation can be now done easily because everything is open. So we can do a lot of innovation in this architecture. Please check Open Lines for more detail. So what are the service classes and the scenarios? So I will go a bit faster because I think almost 1 hour now. So we are moving from real world to the virtual world. So this is the way I see 6G, that everything virtualized. From hardware part, we are going to be a software computer generated working in our telecommunication domain. So digital twin I already talked, so I will not go into more details. These are twins of your physical entity where you need to shape your physical entity to the virtual entity. And then this is a fusion between where you do the fusion of your physical space and your virtual space. For example, your city, you want to do the whole digital twin of your city. So there is steps we need to follow. First, we need to create your spaces, both a world, and then you need to connect with the link with high capacity, low latency, and then you generate the data. You need to optimize data because big data is generating. Then you have to use different machine learning AI techniques to optimize it and re-engineer that back to the physical world, which try to optimize its real parameter according to your virtual world. Because we have a lot of data generating, we know we can easily predict what is going to happen. So this is the backloop will go to the smart physical space as well. Then this is the virtual reality. I will not go to detail. I will mixed reality. This is already okay. And Spectrum, I think, is quite important for the future. Now, if you see that Spectrum is mostly allocated by the regulator, it's like a property or from the government. So I think in future it will be more relaxed. What I am proposing is that we should come with the open spectrum access model. So it can be initiated not by the regulator only, but can be initiated by a machine, because machine is one of the user. It can be a specific user, or it can be initiated by the network, and it can be depend upon your physical space that which the either it's a millimeter, low C, the physics of the wave, and what are the dynamically regulator policies in terms of power, how much power you need to transmit in that area, and its chipset is available. And then you have different sharing model. You can share that model between mobile operator, micro, virtual, satellite, and user, and something which you don't know yet. And then we have accelerator here, which with help of machine learning, we can easily predict that which area you need more spectrum. Because what's happening now that we have the operated by a 6 band of like 20 gigahertz, 100 gigahertz, and that will keep back, and they will paying for that band for contract basis or the option basis for per year part. So that is, I think, more on the dynamic basis. So that is, they are moving their band according to, like at night, the network is not fully loaded, so they can remove some of the band back to them and save some money there as well. So this is the dynamic model, which I think is will be the future. But again, this is the bit harder, because there we need to motivate our politician and the regulator to make that possible, because this is more the regulator part rather than more technical domain. So, and then we have our past, present, future. So as you can see that to going toward any future, we need to define our new use cases which help and improve our human life. That's why we going toward e-generation, because that is our main target, our human beings. So we want to make their life easy. So that's why we come up with the new cases. When new use cases are coming, the technology will be changed. So if you can see that in 2040 and 4G, we have web, application, multimedia. Here we have medium latency, reliability, and throughput, and mostly with data and voice. And then we go for the 2030, where you have very low latency, tactile, and high throughput. And you can see the use cases are changing now. Enhanced mobile broadband, machine type communication, ultra reliable low latency communication as well. And then in the next generation 6G, you can see that our more holographic kind of communication are coming, new services are appearing, teleports, new infrastructure are coming, and you can see that our very low latency, high reliability, and high throughput needed as well. You can see that for every new use cases, we need to come up with the new generations and the new technologies are as well. So these are the three rose petals of our new use case, which we need to figure out and define new technologies on that. So we are moving from 2D to 3D, 2 senses. Now we are using only voice and data, but we have to give with the 5 senses as well, gigabit to terabyte, millimeter to centimeter as well. And then this is the pyramid. You can see that we need new media, new IPs, addresses, architecture, and services as well. So this picture I will not go through. So for example, if in holographic communication is quite important, where we need to transmit our whole human being over the network. So just imagine if it's a 6D image we need to transmit. It's a 6D it rotates, so you can see around 1 terabyte of bandwidth we need to transmit that, and the pixel we need to create is for it. It's not like normal communication which we create with the packets. Here we have to create with a pixel, and each pixel have its own important, like in normal communication, we transmit packet, and if 1 bit error in a packet, we assume that whole packet will be error, and that's why there our main concern is the reliability. But here our main concern is the latency, so we cannot retransmit all of them. If one bit pixel error, we just retransmit that pixel as well. So that's what I explained you, that we are moving from quantitative digitalization to qualitative. In the qualitatively, is mostly latency is the main concern, and each byte have different significance, like each pixel have different significance. We don't need to transmit a whole hologram, we just need to transmit which byte with the error. So this is mostly holographic application, but this is quantitatively we use in 4G to the 5G, where we text and voices are main our senses. So as we are moving toward teleports, so where we have to 5 stars, I don't have time to explain of them, but you can see we started from best effort service, now we move to the teleports. So we are transmitting with our vision. This is the vision where we need to transmit our vision, hear, touch, taste, and smell. But if you imagine that in the beginning when we start 1G and no one thought that we're going to send our voice and picture, but we did it. So I think in the future we have to send our touch, smell, and smell over there. In the end, they are data. We just need to manipulate, and we need to some device on the other side of the world or other side of the receiver where you can feel that, you can see the taste. Like we can develop our artificial smelling senses, we can artificial taste sensors in our phone if possible, but again it will take time. When challenge is that when the guy is moving, holographic images, and you need to feel like it's a real person in front of you. For that is the good way your multisensory communication is now coming also into the world. So I will stop here. I will just go very fast because I don't have time. So sorry for that, because it's quite big presentation. Mostly I take 2 hours. So okay, I'll just go to this slide because this is, I like this slide very much. So as we going toward 6G, I think it's very important we have to take care of our this kind of environmental effect, which is a lot. I mean, very few people know that, because we are technical people, so we don't go more deep into this metal thing. So in the one phone set, you can see that we use huge amount of material which we need to dig from the earth, indium, just to make a touch screen. And if you want to design battery, you have to dig nickel, cobalt from the earth, and similarly different materials. So you can see that almost we have to dig so much metals from the earth, and to digging this metal we consume a huge amount of water because we need to purify it, we need to clean them. The huge amount of water has been also used to clean. And so okay, I'll just go to this slide because this is, I like this slide very much. So as we going toward 6G, I think it's very important we have to take care of our this kind of environmental effect, which is a lot. I mean, very few people, and if one bit error in a packet, we assume that whole packet will be error, and that's why there our main concern is the reliability. But here our main concern is the latency, so we cannot retransmit all of them. If one bit pixel error, we just retransmit that pixel as well. So that's what I explained you, that we are moving from quantitative digitalization to qualitative. In the qualitatively, is mostly latency is the main concern, and each byte have different significance, like each pixel have different significance. We don't need to transmit a whole hologram, we just need to transmit which byte with the error. So this is mostly holographic application, but this is quantitatively we use in 4G to the 5G, where we text and voices are main our senses. So as we are moving toward teleports, so where we have to 5 stars, I don't have time to explain of them, but you can see we started from best effort service, now we move to the teleports. So we are transmitting with our vision. This is the vision where we need to transmit our vision, hear, touch, taste, and smell. But if you imagine that in the beginning when we start 1G and no one thought that we're going to send our voice and picture, but we did it. So I think in the future we have to send our touch, smell, and smell over there. In the end, they are data. We just need to manipulate, and we need to some device on the other side of the world or other side of the receiver where you can feel that you can see the taste. Like we can develop our artificial smelling senses, we can artificial taste sensors in our phone if possible, but again it will take time. When challenge is that when the guy is moving, holographic images, and you need to feel like it's a real person in front of you. For that is the good way your multisensory communication is now coming also into the world. So I will stop here. I will just go very fast because I don't have time. So sorry for that because it's quite big presentation. Mostly I take 2 hours. So okay, I'll just go to this slide because this is, I like this slide very much. So as we going toward 6G, I think it's very important we have to take care of our this kind of environmental effect, which is a lot. I mean, very few people know that because we are technical people, so we don't go more deep into this metal thing. So in the one phone set, you can see that we use huge amount of material which we need to dig from the earth, indium, just to make a touch screen. And if you want to design battery, you have to dig nickel, cobalt from the earth. And similarly different materials. You can see that almost we have to dig so much metals from the earth, and to digging this metal we consume a huge amount of water because we need to purify it, we need to clean them. So huge amount of water have been also used to clean. And thirdly, these metals are not coming from one country. Some are come from China. China is the biggest one with nickel and cobalt, but other countries also, South American produce also. So a lot of things we need to be careful. So it's very important we need to check also this environmental effect and also try to decrease the communication cost, and plus try to use the metals which is easily available, and also not use so much water because water is one of the biggest crises coming in the future. So I think we have to take care of that part as well. Again, these are mostly from material sciences, but as a communication engineer, we should also aware that our phone consuming a lot of material to create that, and whole need a lot of effort. Or we try to reuse them in some way. I don't know now. To when we our old phone set, they are, and we can re-engineer them, use again. So that's, I don't have time to explain. So that's all from my side. Thanks a lot. So if you have some questions, so feel free to ask now, please.
So, Dr. Mumtaz, very interesting talk, exposing so many topics within what do you think that it will be 6G. Thank you for the nice presentation. Now time for questions from audience, comments.
Yes, I just want to comment one because next time maybe I can give talk because very long presentation. Mostly I take 2 hours as I explain you, so I have to skip a lot of slides.
Yeah, but also if you would like to share your slides, we can also post them on CSIM website.
Yeah, because some are confidential, but I will remove them, then I will send the rest of them.
Thank you very much. So for the audience, if you don't want to ask yourself, you can write it also on the chat, and we will ask the presenter. So I have a couple of questions, if you allow me. So the first one is, I'm interested in AI impact on 6G, but to better evaluate it, I will use the benchmark of AI and 5G, and this is my question. How do you think that AI is doing so far in 5G and in actual implemented systems?
I mean, as I explained you that in the beginning, that as a wireless engineer, we are putting AI in every area without knowing it is going to affect or not. Because a buzzword we are using a lot. And I explained you, we cannot use AI where we have a closed form expression because very few people know this about this. But if you want to use a physical layer, of course, you can use in a certain way, like channel estimation, beamforming, where we don't have a closed form expression. The best box where you use machine AI is the upper layer, application, transport, core part, where you can easily use that, because on that we don't have anything called closed expression. But on the physical layer, still it's the challenge to do that, and that is from the side from this academia that we are using that. But from the, if you talk about this industry and standardization, still we are lagging behind, because in Raleigh 17 we have workshops, we have proposed, but again the same thing for proposing there as well, challenge estimation, Pari coding, the normal words. But which part of machine learning is to be standardized, that is difficult to answer. Like it's the good example of that. If you see the in the normal wireless communication, we have different scheduling algorithm. Like you are very familiar with that. You have round robin, MaxCI, and proportion fairness. So this is all depend on the vendors. For example, this Huawei use PF, proportion fairness. Nokia use MaxCI, but this is their criteria. We cannot change because they come and the standard didn't tell us we have to use, because this is all depend from the vendor. So there is no standard of the scheduler. So same like with the machine learning. So everyone is, it will be as a black box that inside maybe supervised, unsupervised machine, or we don't care, and the standard also don't care. But standard care, what are the interfaces which is going to connect this data coming to my RAN, or that is the main part. And this is a challenge which we need to solve in SAGE.
Mm-hmm. So commenting on that, so based on your connections with industry, so what is the feedback? It is still a buzzword that they have not seen.
Yes. It is a buzzword, and that's explained that we cannot use machine learning everywhere. Of course, to write papers look good, but it's nothing to do with the real world. We can, for writing is very good, but not for real world.
Okay. Most probably, in computer science, it's widely used, I think, with databases and so on. Yeah, but in communication world, maybe it is a bit more challenging. One thing that I would like also to ask you is about the RIS, so these smart meta surfaces that they will do the reflection in non-Snell law based, so we can control how they will do the reflection. What do you think that do you think that they will have a big role in 6G, 5G, beyond 5G?
Yes.
About them?
Again, I will stand from the standard. So it is already proposed by many companies in a workshop in Raleigh 17. So definitely it will be part of standard, because what this industry look it as a node to be in the network. They just see there's a new node coming into network. Like if you remember this Raleigh communication, cooperative Raleigh's communication in Raleigh 16. So I think more or less it will be the same. They come the new entity inside our network, like base station, relay, mobile, intelligent reflected, and again now they're going to propose different signaling mechanism for them. So that will be for sure. That is the easiest part to be part of this industry from intelligent reflected surface.
Thank you. It's very illustrating talk. Very large number of topics that to be discussed, to be seen which ones will have their path into the 6G standard.
Yes.
So no more questions on my side. So I think nothing received also from the audience. So I think that it is time to close this talk. To thank you again for accepting our invitation. It has been our pleasure to host your talk, and we will be posting after your kind approval to record. So we will be posting the recording for the video recording on our YouTube channel and sharing it with our community.
Okay.
So thank you again.
For all of you guys.
Yes, thank you all, and thank you for the audience to join, and we will let you know about future seminars within the CSIM series for online seminars. Thank you all.
Thank you. Bye-bye. Cheers.
Thank you. Bye-bye.